So we're going to go ahead and get started, and I will introduce our first speaker. I'm going to try this. Dr. Dzwonkowski. Yes. So he is an assistant professor in the Department of Marine Sciences at the University of South Alabama, where he's been a faculty member since 2014. He completed his PhD at the University of Delaware and his undergraduate studies at the College of New Jersey. And his research interests lie in coastal physical oceanography, as well as how physical process impact biogeochemical cycling and ecosystem function. So he's going to come and kind of give us a background on estuaries and some of his work. And so if you don't mind coming on up, then I will get you started.
Yeah, my gosh, estuary circulation in 20 minutes. My gosh, there are textbooks, volumes on this topic, so it is quite a challenge.
We like to challenge our speakers.
Quite the challenge to get estuary circulation in 20 minutes. So, and then never mind throwing in a little bit of new research. Oh my gosh. So we'll see how I do. I know there's a clock ticking, so hopefully I don't run over. We will see. I did try to make it relatively concise. Yeah, so thank you for that introduction. Thank you for inviting me here. The title of my talk here, or this little bit is, estuaries and their exchange with the shelf and implications for oil spills. And a lot of my work isn't necessarily directly with oil. It's basically circulation processes that could move oil around. So a lot of what I'm going to tell you about today is just how estuaries work and how an understanding of how these estuaries can work can link to better oil spill responses. And so the first part of the talk is all just going to be about estuary circulation, how that connects to the shelf, and then the last little wrap up is going to be sort of creating linkages to oil spills and how an understanding of the system circulation could influence how we respond to these, or where potential threats are, or areas that are likely to be threatened by oil spills. And in particular, as this sort of probably famous image shows, that the oil spills that we often get in the Gulf of Mexico are from offshore, right? We have a lot of rigs, we have a lot of petroleum industry going on offshore, whether it's the oil or gas industry. And so oftentimes the threat of oil spills is going to be coming from offshore rather than within the system, although there are clearly threats within the system with shipping industry and things of that nature. But I'm going to focus primarily on some of the offshore implications for how spills can get into estuaries with estuary circulation in mind. So motivations, I kind of hit on that already, but the goal here is to improve the understanding of physical processes that impact the strength and structure of estuary circulation. Why do we care about estuary circulation? Well, understanding how things move, where things go, has direct ties to a lot of ecosystem function, a lot of biogeochemical processes. And so sort of the ground level layer of what biology is operating in is the physical environment of the system. And so knowing how that's changing over time is going to inform ecosystem behavior and ecosystem dynamics. So the primary objectives are discuss some general aspects of estuary circulation, improve the understanding of connectivity between the offshore shelf conditions and how the offshore shelf conditions can potentially affect the inshore estuary, and then talk about how these estuary shelf exchange can have oil spill implications. So with that, sort of the bare bones, most basic sort of look at estuary circulation, sort of this classic two-layer structure where you have river input at one end. Yes. Yes. So you have river input on one end, and you have a marine influence, saltier water. Can you guys? Oh. Yes. So saltier water on one side. So you have two things operating here that really drive this. The result of river discharge and the oceanographic conditions lead to this two-layer structure where you typically have outflow at the surface, inflow at the bottom. And again, keep in mind, this is after we've averaged out the tides. So usually in most systems, the first order currents in an estuary are tidal. Depending on whether you're in a diurnal or semi-diurnal, you have 12 hours in, Mobile Bay, 12 hours out. It's a diurnal cycle in sort of the northeast of Florida. You have semi-diurnal system, 6 hours in, 6 hours out. But if you average over the tides, you you get a structure that's going to look like this, where you have outflow at the surface, inflow at depth. And that's really driven by two things. It's driven by river input. The river input generally just tries to push stuff out of the system. But the density difference between the fresh water and the salty water creates a two-layer circulation where you have outflow at the surface, inflow going, coming in at the bottom. And the two aren't unrelated. The more difference you have between the fresh water coming in, the saltier water offshore, the stronger that two-layer circulation. And so the two are not independent of each other, they're coupled. And so that's sort of the order one estuary circulation. Right? This is classic sort of classic estuary circulation. But the reality is systems are very different, right? So not all systems are the same, and this sort of just gives you an idea of different types of system and what the circulation might look like. So there's certain classes, because it's a chaotic world out there, we like to put things in boxes, right? There's all these different estuaries out there. We try to put them in boxes. Some of the boxes these are four sort of typical boxes that you'll sort of put a type of estuary in. You have things like salt wedge, partially mixed, well mixed, vertically, well mixed, vertically and laterally, right? Each one of these plots, right? So the top plot is a vertical slice. The bottom plot here is sort of an overhead look at the estuary, where that would be the river, this would be the mouth, river, mouth, and this is sort of taking a vertical section through that system. And the main take-home point here is there are subtle differences in each one of these. So it's not a one-size-fits-all. The circulation in a given system is going to vary. So while I would love to tell you every system works like this, a lot of systems do, but there are exceptions to this, and they don't always quite look like this, right? And so the type of circulation you're going to get in estuary is going to vary depending on what type of system you're in. And there are a lot of types of systems out there. So do any of these systems, so of these sort of classic estuarine circulation, do any of these systems look like Mobile Bay? And Mobile Bay, what do we have? We have one main input here. We have one side channel there. So there's two areas where you can exchange. It's broad, you have barrier islands, right? That doesn't look anything like your sort of classic setups here where you have these wide mouth systems. There's no barrier islands here. And so fundamentally, these sort of illustrations of what circulation might look like are going to hold up to some extent in a place like Mobile Bay or a similar type system, but there are going to be some differences because of the constraints of that system. And so the main take-home message is the circulation in a given system is probably going to be different from a classic or a sort of idealized look. There's a lot of complexity out there, right? I mean, we also have this ship channel, which is kind of hard to puzzle out how that's going to influence circulation. There's a lot of variability here. That's just spatial. We have other things to play around too. Tides, winds, river discharge, all those have a time. Right? There's spring tides, there's steep tides, there's windy days, there's not windy days, there's droughts, there's floods. All those things are going to change what these sort of circulation patterns look like. And so there's a lot of variability in these systems. And the hope is to find some kind of general characterization where we have some rough understanding. But if you really want a very detailed understanding of where things are going to go and how things are going to move, you really need to talk to a regional expert or something that's got a very particular model simulation for that given area. The general principles, you can get something out of general principles, but to get exact predictions on where things are going to go, you really have to be thinking system specific. Similar thing goes for how the end member, the ocean end member out here, how is that going to be contributing to what's going on in this estuary? And there's a couple ways that can happen. So a couple of ways are geography, right? So, or it's not geography, geomorphology, right? Where you have sort of a mouth and you have a ship channel in Mobile Bay, so you have a narrow mouth that might constrain exchange with the Gulf. But you also have a deep ship channel, which, because of the depth, will likely encourage exchange with the Gulf. So the morphology of the system is going can affect how much the shelf conditions are influencing the estuary. Another thing that can influence how much the shelf play a role is this thing called upline or downline. And this has to do with wind conditions on the coast, sort of moving the picnic line up or down. So when you move the picnic line up, you allow colder, typically nutrient-rich water to move closer to shore. And under the opposite conditions, downward conditions, you're basically pushing surface water down and around, moving that colder, typically more nutrient-rich layer offshore. And so depending on whether you're in a state of upline or downline, the conditions that the estuary mouth has access to could change quite significantly, which is what we're going to talk about next. So both circulation in a system and circulation and its connection to the shelf are going to depend on the system characteristics. And depending on what kind of system you're in, there can be quite a bit of variability there. So looking at the Mississippi Bight, back in 2016, and this is sort of a case example of how the shelf conditions could be influencing water quality in a place like Mobile Bay. So back in 2016, I was on a part of a project funded by Dauphin. It was called the Concord Consortium, where we did a bunch of surveys. In this Bight, coloration here is chlorophyll concentration. And this close to shore, this is really a proxy for fresh water. So where you see the yellows, that's just showing you it's probably very fresh water. The blues are more salty water. But you can see there's a lot of complexity here in the structure of that chlorophyll concentration, which is effectively a proxy for fresh water. And if you look at these three transects that we did, if you look at the dissolved oxygen on the shelf, what you can see is there's a lot of spatial variability in the dissolved oxygen, where the western corridor here has a lot of hypoxia. The middle corridor here has low dissolved oxygen, but it's not hypoxic. And the eastern corridor here has near hypoxic conditions. The color map here is dissolved oxygen in milligrams per liter. So there's a lot of variability in the shelf and what the shelf is doing. But you can imagine that depending on where this low DO is, it may or may not be able to get into your estuary. So this sort of represents somewhat like oil, an offshore thread to the water quality in the estuary system. And so during this 2016 year, we happened to be doing some work in Mobile Bay. And we can look at what was going on in the bay and how this offshore water was being, how this offshore condition was impacting our estuary. And so during this time period where we saw a lot of shelf hypoxia, we were doing sampling in Mobile Bay. So this is kind of a setup of, we have a bunch of transects. We're going to be focusing on the ship channel, but we have a long-term monitoring station offshore, and this data, this station collects hydrographic data in a time series form. So what does that look like? Well, we have depth. So this is on 20-meter isobath. So we go from the surface down to 20 meters, and then we have time along the x-axis, and the coloration is water temperature. Right, so in the first portion, so this goes from June 2016 to August of 2014, August 14th of 2016, and the first part here is a strong upwelling, and so that's sort of, this is pointing this arrow. You have this cold water coming up very close to shore, and it sort of upwells. It comes up and around. You can see the isopycnals here. The lines of, these are actually isotherms. The lines of constant temperature bend upwards. In the opposite case here, where you see the surface red, this upper layer is very warm. This is a downwelling period. And if you look at spatially what's going on the shelf, you have water going onshore, coming down and around. The isotherms bend downward, not upward. So this fundamentally changes. So if you have your mouth of your estuary here, it can get at cold water here versus that cold water is being pushed offshore, and so it doesn't have access to that bottom water from your downwelling. And so the next question is, well, what does that mean for the shelf? What does that mean for the estuary? Well, if you think about the previous slide, where we noted all this low dissolved oxygen on the shelf, this low DO condition on the shelf could potentially get pulled into the estuary. And so if you look at the shelf conditions over time, so this is sort of the dissolved oxygen conditions. So these are all transects from these are CTD casts, so it's just basically a measurement of a parameter with depth. So this is temperature with depth. This is dissolved oxygen with depth. And from blue is upwelling to red, which is transitioning into downwelling. And so you can see the temperatures go from a large area of cold water. That cold water is basically reduced in size, and that corresponds to a change in the oxygen condition, where you have this big area of, this big bottom area of low DO, and that becomes much more aerated as you go from blue to yellow. And so the shelf condition changes dramatically whether you're up on or down on the phase. And so what does that mean for the estuary? Well, if we look at the conditions at the estuary, at the mouth of Mobile Bay, we have a long-term monitoring station called Dauphin Island. So this measures water quality. And what we can plot up is the, we focus on this one for time constraints. This is basically a plot of probably about, I think it's about 13 years, 13 Julys worth of data where we have dissolved oxygen and temperature. And what you can see here, particularly in the red, is during upwelling conditions, there's a trend of lower DO, so lower DO and colder temperatures. So you have high DO going to low DO during these upwelling conditions. And so that suggests that when you have upwelling, you typically have lower dissolved oxygen being pulled into the estuary. So that upwelling condition is linked to lower dissolved oxygen at the mouth. Why is that bad? Well, if this low DO water gets in the ship channel, so this is sort of some surveying that we did along the ship channel at the same time period. So these black lines are days when we're out surveying this section of the channel. Again, this is the time series out at focal, upwelling, downwelling, upwelling. And then if you look at sort of the transect along the bay from basically the mouth E, so this is sort of Mobile Bay, so this is E to A, we're going to look at sort of what that transect looks like. And so what we're able to do with these surveys is catch a mass of cold water. So this is sort of what the raw data looks like. Not to bother you guys with that. We're just going to look at this nice cartoon. So this is offshore, this is cold water. This cold water gets pulled into the bay, that's what this sort of indicates. And over the course of this sort of 10-day period, this mass of cold water gets pulled into the system and eventually dissipates. And so why is that important? Well, it's linked to dissolved oxygen. So depending on whether or not you have an upwelling or downwelling phase, the dissolved oxygen, so this is distance from main pass, this is the water transect. The colored line indicates different days, and the y-axis is dissolved oxygen. So what you can see here is the days when it's not upwelling favorable conditions on the shelf. You have relatively well-oxygenated conditions in the ship channel. So you start out at the mouth at like 4.5 to 5, and over the course of that, over the length of that ship channel, you never get below hypoxic conditions. The one day we're sampling during upwelling, we started out at the mouth at much lower conditions, and that subsequently was able to drop. As the water works its way up the ship channel, the respiration of the biological components in the estuary pull the oxygen level down and you get below hypoxia. And so that offshore end member here really dictates whether or not the ship channel is going hypoxic. And so the fact that it's pulling low DO water from offshore sets the sort of boundary condition at the mouth of the estuary that then is pulled in, and because of the estuarine circulation where water is drawn in at the bottom, that water is allowed to go hypoxic because it does not have contact with the surface. So what does this mean for oil spills? So DO can be thought of as a proxy for oil, right? It's just sort of something that we were tracking that is in the water column that could get into an estuary through subsurface beams. So something like the Deepwater Horizon, where you had subsurface oil on the shelf, you need to think about how that estuarine circulation is going to be impacting the estuary, right? So some classic pictures, so I think I should time this okay. So some classic responses during the Deepwater Horizon were let's turn on the water spigots and push all the fresh water through these systems and have it prevent oil from getting into these estuaries. And, this is sort of a nice map by this guy, Raw, where you see sort of plumes of fresh water coming out and oil sort of hits the sort of freshwater boundary. And in some cases, that was pretty effective. As you can see here, what happens is oftentimes it gets redirected and it's gonna hit the shore in a different place. So it's just kind of like pushing the problem to someone else's beach. But the other thing that you have to consider with an offshore oil spill is this subtidal circulation. So if you ramp up the freshwater discharge, you're creating a stronger density gradient between the head of the estuary and the ocean. The stronger that density difference is between the freshwater and the ocean water, the stronger your subtidal circulation is going to be, the stronger your pull into the estuary from, say, a ship channel is going to be. And so by ramping up the freshwater discharge, you're also ramping up the subtidal circulation, and this bottom water could be pulling more subsurface oil into your estuary. So you sort of have you may be pushing water out of your system at the surface, but you could be pulling it in at depth where it may be more difficult to capture, and you might have a more difficult time to figure out where it's going to go and how to respond to it, and it's sort of pulled in at a subsurface level. And so with that, I am done. Just sort of acknowledging some support. Gold-Marie, tech support at GISL was very helpful. And if you want to know more about any of the work that was shown, we have a couple of publications out in Continental Shelf Research, Journal of Geophysical Research. And so this stuff is out there in the public domain. So there's a lot more detail in that stuff.
Thank you.
Yeah, you're welcome.